So we currently know that we can find a series for a function, and on the interval of convergence, the series and the function will be equivalent to one another. However, as soon as you cut off the series, or as soon as you truncate the number of terms that you're using, there's going to be an error. So anytime we do an approximation, we want to talk about quantifying the error. We already know that if our series is alternating, the maximum error is the magnitude of the first neglected term. So if the series is alternating, we already know how to quantify the error. However, if the series is not alternating, we're going to use something called the Lagrange error bound. So when you look at this, the information in this box, it might be a lot to look at, but the Lagrange error bound is actually similar to how we determine the error for an alternating series, but there is a caveat. So let's just talk about what we're reading here in this box. So we have a polynomial, so P sub n is a polynomial, and it's centered at x equals a, so it's centered at a. And we're using that to approximate f of some other value. So we're using that to approximate our function f at some value c. So the error for this approximation, notice that like on the left, we have the polynomial at c. So really, that's going to be our polynomial approximation. So this is our polynomial approximation. And what we're subtracting from that is the actual function value, f of c. So that's our actual value. So in other words, the left-hand side of this is just the error itself. And we can use the absolute value there because it doesn't matter if the difference is positive or negative, but the difference between our approximation and our actual value, that's our error. So the Lagrange error bound tells us that our error is less than or equal to, well, all this junk on the right, this other thing. So first, let's notice that for our polynomial, this is P sub n. So for our polynomial, we're looking at like the nth term. So when we look over here, notice that this is f to the n plus 1. We have all these n plus 1s. So if my polynomial is the nth term polynomial, I'm going to be looking at the n plus 1 term. So otherwise, though, this is a lot, or in that way, I should say, this is a lot like our alternating series. So if we're using our nth degree polynomial to do our approximation, we're going to use the n plus 1 degree term. In other words, the next term. So a small difference is that we're not evaluating the n plus 1 derivative. We're evaluating it at z. And z is some number. So like our z here, this is going to be some number between the center and and where we're stopping. So between the center and where we're using it, so our actual function value, I should say. It's going to be some number that makes the nth derivative as big as possible. So we want to choose a z, or we want to use a z that will maximize this derivative on the interval that's from the center, because we said we're centered at a, to the actual input c, like where we're evaluating our approximation. So our Lagrange error bound is just one more, time to clarify this. It's not something that we use for an alternating series. So if our series is not alternating, the error must be less than or equal to our first neglected term, except that we need to find the maximum value of the n plus 1 derivative. All right, so to just see what this looks like in an example, these examples are going to be like sample FRQ questions. So in these examples, these are all kinds of things we might be asked in a free response question. All right, so notice in this first one, we're given a function and we're given its series, and we're told that the radius of convergence of the series is 3, and we're asked to find the interval of convergence. So we don't need to do the ratio test. We could, but what would save us some trouble here is to recognize first that this series is centered at 2. So our center is at 2 because I have an x minus 2 in my series. And if my radius of convergence is 3, I could just think on my number line, if I go to the right 3, I would be over at 5. And if I go to the left 3, I would be at -1. So my interval of convergence is going to be between -1 and 5. However, we still have to check the endpoints. So I can skip the ratio test with the information I'm given, but I would still need to determine if my endpoints are on my interval. So when I check for x equals 1, x equals -1. Well, -1 minus 2, that becomes a -3. I have -3 to the power of n. And 1/3 to the power of n times -3 to the power of n, that just becomes a -1 to the power of n. All right, so -1 to the power of n, that diverges. Like as I plug in greater and greater values for n, that's going to just oscillate between -1 and +1. So really that diverges by the nth term test because my limit would not go to 0. All right, so I also need to check the endpoint x equals 5. All right, so again, I'm going to plug in 5. Oops, that's 1/3. 5 for x. 5 minus 2 is 3. So this becomes 3 times 1/3. That just becomes 1 to the n. And that also diverges. We could think of that as that diverges by the nth term test. The limit as n goes to infinity is not 0. So we did have to check our endpoints, but our interval of convergence is from -1 to 5, excluding the -1 and the 5. All right, so part B, we are asked to use the first 3 terms of the series to approximate f of 2.5. And again, I would want to make sure 2.5 is on my interval of convergence, which it is. It is a number that is between -1 and 5. So to do that, f of 2.5 would be exactly equal to our series. So I've got 1/3 to the power of n. When I plug in 2.5, 2.5 minus 2 is 0.5, or 1/2. So I get a 1/2 to the power of n there. And I could go ahead and multiply that, and that would become 1/6 to the power of n. So I just need the first 3 terms. So that's 1/6 to the 0 power plus 1/6 to the first power plus 1/6 to the second power. So really that is 1 plus 1/6 plus 1/36. So if we get common denominators there, we end up getting 43/36. All right, finally in part C, we're told that it is known that the third derivative of f at z, the magnitude of that, is less than or equal to 4 for all values of z between 2 and 2.5. So notice this was like my center, and this is 2.5, is where I was just approximating my, I was approximating f of 2.5. We're asked what is the maximum value of this. When we see this, we just have to recognize that this is the error. So it's asking us for the maximum value of the difference between our polynomial approximation and our actual value. And that's what error is, the difference between our approximation and our value. All right, so this is asking us for the maximum error, and we can see that this is not an alternating series. Our first three terms were 1, 1/6, and then 1 over 36. So our maximum error is going to be found using the first neglected term sort of. So when we found our approximation, we used n equals 0, n equals 1, and n equals 2. So my maximum error is going to involve the third term where n equals 3. So it's the third derivative at some value. So the third derivative at some value over 3 factorial. And then I'm going to multiply that with my x minus 2. So I'm going to plug in my 2.5 minus 2. And this is going to be to the third power, right? So our maximum error is going to be less than or equal to this magnitude. And again, that's just what we're seeing up here in our box. All right, so notice that in the prompt here, we are told that it is known that the magnitude of our third derivative at z is less than or equal to 4. So 4 is the maximum that our third derivative at z could be. And so that's what we're going to use when we're calculating our Lagrange error bound. So really, I'm going to plug in a 4 for my third derivative. And let's see, 2.5 minus 2, that's just really 1/2 cubed. All right, so we get 4 over 3 factorial. So that's, let's see, so that's 4/6 or 2/3 times 1/2 cubed, so times 1/8. I get 1 over 12, 1/12. So our maximum error is less than or equal to 1 over 12. All right, on page 105, go ahead and try to do as much of this example as you can, and then check it using the video. All right, in part A, we're going to find the interval of convergence. So I know I need to do my ratio test here. All right, so I need my n plus 1 term. I'm going to multiply by my reciprocal of my nth term. So when I simplify this, I'm going to get x times n over n plus 1. And again, since this is a limit involving n, I could pull out my absolute value of x. I'm going to multiply that with my limit as n approaches infinity of n over n plus 1. All right, and the value of that limit is just equal to 1. So I get my absolute value of x times 1. Must be less than 1 because again, my ratio needs to be less than 1 for convergence. So I get x is less than 1 but is greater than -1. And I still need to go ahead and check my endpoints. So when I check x equals -1, so that just becomes -1 to the power of n over n here. So this is an alternating series. If I look at just its absolute value, I would have 1 over n, which decreases to 0. So I know that this series converges by AST, the alternating series test. I also need to check my other endpoint, x equals 1. All right, so when I do that, I just get 1 over n. And this is our harmonic series, and we know this diverges. So this diverges by p series. So our interval of convergence does not include the endpoint 1, but does include the endpoint -1. In part B, we're asked to find the series for g prime of x. Well, what we were given was the series for g of x. So there's more than one way we could do this. I know that g prime of x, well, that's just the derivative with respect to x of g of x. So like one way we could do this is we could actually write out several terms and kind of see this pattern here. So if I look at the terms of my series for g, when I plug in a 1, I get x to the first power over 1, so that's just an x. When I plug in a 2, I get x squared over 2. When I plug in a 3, I get x cubed over 3, and so on. So we could actually take that derivative and we would get 1, let's see, we're just using the power rule here. So then I would get 1 plus x squared plus x cubed when I take that derivative of those terms. So we could do that, and then we could go back and try to write the series from that. But what might be easier is we could actually just take the derivative of our series in summation form. So when we take the derivative, remember that we're taking the derivative with respect to x. So I'm just going to treat n like a constant. So really, this is just the power rule. So my exponent n would pop out. I would get an n minus 1 on top. And when I divide that by n and I simplify that, I would just get x to the power of n minus 1. So as I plug in like 1, 2, 3, etc., my first term is going to be x to the 1 minus 1, or x to the 0, which is just 1. My second term is going to be x to the 2 minus 1, which is just x. My third term will be x squared. My fourth term will be x cubed. So I can take my derivative in that summation form as long as I'm careful and I'm taking the derivative with respect to x. All right, part C, use the first two terms of the series from B to approximate g prime of -1/2. Well, I'm just plugging in -1/2 for x. Well, my first term was a 1, nothing to plug in. My second term is a -1/2. So my answer here, my approximation, is 1/2. That should be approximately equals. I don't know if that matters that much. All right, lastly, part D. What is the maximum error that arises from this approximation? So again, if I think about g prime, so my g prime of -1/2, let's get a few more terms. So I'd have like a 1, then a -1/2, then I would plug in a -1/2 squared, which would be a +1/4, then a -1/2 cubed, which would be a -1/8, and I could keep going and going and going. We'll notice that this is an alternating series. This is something where I do not need to use the Lagrange error bound. So if this was an alternating series and I use the first two terms for my approximation in part B, then my maximum error is going to be the magnitude of my first unused or neglected term. So the magnitude of 1/4, which is just 1/4. So my maximum error, or my error, I should say, is going to be less than or equal to 1/4.